Hey guys, this is Mr. G coming at you again. Hey, today we'd like to look at type 2 trajectories, projectile motion, and solving several problems. This would be on page 6 of the type 2 and 3 notes. So I've got a couple pages here of the notes that have type 2 problems. Page 6 in on that today with the notes, and then on another video I'll do type 3s. And so why don't you go to page 6 there from your new note packet. In on that today with the notes, and then on another video I'll do type 3s. And so why don't you go to page 6 there from your new note packet. And boy, I don't know how to say this, kids, but type 2s and type 3s can be a little bit challenging to work. And so I'm going to show you I'm going to kind of show you a little bit about how to work through these problems. Again, grab a calculator, make sure it's in degrees and not radians. Nick the Kick punts a football with an initial velocity of 25 meters per second. Okay, I'm going to circle that. That's important information here. Let me get my pen working here. Okay, so that would be our VI. He kicks this ball with an angle of 40 degrees, so there's our theta. Determine the time of flight, or what's called the hang time. So if you're into football, punting, or whatever, you know, we call that the hang time of the football. The horizontal displacement, also called the range, so that would be your delta x. We'd also like to get the maximum height or altitude of the football. That would be our delta y. With some sports, the height of the ball counts, like if you're kicking a field goal or something like that. Now, so what we've got then is a type 2 trajectory here. So what we might really say here is he's kicking it, and then it's being caught by somebody who's about the same height. So we've got then this full symmetry, or this parabola, and the beginning and ending heights are the same. So really then kind of what we want is we want to basically get how far forward the punt goes. We want to get the height of the punt, and we want to get the total time, also called the hang time, that the ball's in the air. All right? Now, so what we've got really given to us, we know how fast the ball's being punted. Okay, that's 25 meters per second, but it's being punted at an angle of 40 degrees, so that'd be considered our theta. All right, so that's really all we know, but we're still going to be able to solve the problem. Now, let me just take this bit of the trajectory and let's kind of highlight what's going on here. See, I'm creating a triangle, a right triangle there, right? So we know really the hypotenuse is 25 meters per second. Now, this would be our velocity, our initial velocity in the x direction. This would be our initial velocity in the y direction. So what I'm going to do is bust this velocity up into its two parts, Vx and Vy. Now, this is the adjacent leg, so we would say 25 cosine of 40. And here we'd say 25 sine of 40. Okay? So again, that's back to our unit on vector mathematics. So when we put all this in our calculator, 25 cosine of 40, 25 sine of 40. Again, you got a calculator there. You can check my numbers. But we get around 19.15 meters per second there. And for this one, we get 16.07. All right. Now, in the x direction, the ball's going to stay constant velocity. All right. We kind of know that. In the y direction, the ball's going to go up, 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 but it's going to slow down. It's going to reach the apex, what we call the top of our trajectory, and then it's going to start coming down. All right? Okay, well, let's look at the time of flight, the hang time. Okay, the hang time really is determined then by, you know, by a vertical sort of motion here. So I'm going to write the how far equation. Okay, I'm going to write the vertical how far equation here. So it's delta y, or that's really yf minus yi, all right, and that's going to equal to VIYT plus 1/2 AT squared. Okay, you got it there? Now, with the type 2 parabola, it starts and finishes at the same altitude, or at the ground here. So we can say then that this delta y, or yf minus yi, really is equal to 0. So I can equate then the right side here to 0. VIY, though, we said was 16.07 t, then plus 1/2. Well, we know then the object's in free fall, right? Gravity's pulling down on it, so we'll call that negative 9.8, and we'll put t squared there. Now, we can do a little bit of simplifying, so we can say then, and I'm going to put everything really on the left side, so we can really say then that 4.9 t squared minus 16.07 t equals to 0. Everyone okay with that? Now, what we can do is factor out a t here. Okay? Just basic mathematics here. We really then have, again, we have a quadratic, so in this case we've got two solutions. Okay, our first solution would be time equals 0. Okay, and then we've got this other solution here. Okay, we can put this on the other side. Okay, follow the mathematics, please. Divide through by your 4.9 both sides. And then we have our time that's equal to 16.07 divided by 4.9. Now when you do that in your calculator, you should get around 3.28 seconds. Okay, so really what do we know here? Well, there's our trajectory. We know then at time equals 0, there's your first solution. Time equals 0, we're at the ground. Okay, and then time equals 3.28. We're back at the ground. So that would be considered the hang time. Okay, that's the hang time of the football, 3.28 seconds, all right? Well, now let's look at the horizontal range, or the displacement, okay? That's a delta x idea, right? We said delta x then is our Vx times t, right? Where that t then is just what we found here, 3.28. Well, we know what the Vx is. It's 19.15. Okay? And this time here is 3.28. All we have to do is product those two things. Okay, look, our seconds cancel and we're left with meters. Okay, 19.15 times 3.28. We get around 62.8 meters. Okay, so in football terms, a meter and a yard are pretty close. So around 63-yard pond. That's a pretty good pond, isn't it? All right. Well, the other thing we'd like to find really is how high, what's the maximum altitude? That'd be a delta y idea, right? What's the maximum altitude of the football? Right? Now, for a symmetric parabola, we know the total time is 3.28 here. So for a symmetric parabola, this maximum altitude will occur at 1/2 the time, right? Do you understand that? So it's going to take half the time to get up to this point and half the time to go back down. So at exactly half time, we're going to be at our maximum altitude. So what we can do is take 1/2 times our total time, okay? And we can get the time that we need to put into our how far equation. Okay, so we take 1/2 of 3.28. What is that? About 1.64 seconds. So we rewrite our how far equation, right? Our vertical equation, delta y equals VIT, that's in the y direction, plus 1/2 AT squared. Again, that's our how far equation. We'd like to now solve this for delta y, right? That's the maximum altitude. So we need our VIY, which we said was 16.07. Okay, we'll put in then 1.64. We'll take plus 1/2 times negative 9.8 times our 1.64 squared. All right, so hey, this is the one equation that a lot of kids flub up on. Okay, a lot of stuff going on here. You need to be kind of careful. Do it out in steps. Okay, so I'm going to multiply the first two numbers. I get 26.35. Then I want to multiply 1/2 times negative 9.8 times 1.64 squared. Okay, so I get 13.18 for that term. and delta y then is going to be about 13.2 meters. So that tells us the ball gets about 13.2 meters high. All right? A lot of type 2s can be worked in this fashion. I'm going to work another one here for you. So why don't you go to page 7.
Okay, so I've turned the page now. I'm on page 7 of the note packet here. And let's do another type 2 trajectory here. So this is a shot put problem, and this is from Blake, a Lawrence High graduate. So he set the school shot put in 2011. I didn't see the actual throw, but we can maybe work a problem with some data that might be pretty close to reality here. So he throws this shot put with a velocity of 14 meters per second. So that 14 meters per second, that represents a VI at an angle of 50 degrees. So that would be our theta. We want to determine the time the shot puts in the air, the range or horizontal distance of the throw, the maximum height. Assume full symmetry, so that's telling us it's type 2. So even though he's probably throwing the shot put from his shoulder or from the top of his chest really, and it hits the ground, that would really be a type 3 trajectory. But we're going to call it a type 2 just so we can work the problem. So there's our parabola, and then our shot put's going to then move with a VI of 14 meters per second. So that's going to be then that vector. And the theta then is 50 degrees. Okay, so at the very beginning, if I want to redraw these vectors here, I would have then a VI, that's going to be my 14 meters per second. And then a VIX, that's my initial velocity in the x direction, or my forward speed. That's going to be our 14 meters per second times the cosine of 50 degrees. Okay, when I work through those numbers, I get then 9 meters per second. So we know then, let me do this in another color here. I can grab another color here. We know then that the velocity in the x direction is not going to change. So that's going to be then 9 meters per second throughout the whole trajectory. The upward velocity then is based on a sine of 50 degrees. So that's going to be our 14 meters per second times the sine of 50 degrees. So our VIY then is 10.7 meters per second. So the object, the shot put's going to start at that velocity. Let me turn colors again here. It's going to start at that velocity, but it's going to get smaller. That velocity is going to get smaller as it goes up because it's in free fall upward. So gravity's pulling down on the shot put. At this apex then, which is our kind of bilateral apex line, we have motion up and then motion down. So at that point there, our Vy at the apex is going to be then 0 meters per second. So it's going to start at 10.7 meters per second. It's going to get smaller and smaller. And finally at that apex, it's not moving vertically at that instant. Then on the way back down, our velocity starts small and will gain speed downward. And that shot put's going to start at 10.7, but it's going to finish up then at negative 10.7 or 10.7 meters per second downward. So that kind of represents my velocity vectors. So let's do part A first, the time the shot puts in the air. So we can get then the time it takes to get to the apex. So let's look at then the time to get to the apex. Because we know then we can use symmetry. Once we get the time to the apex, then we can multiply that time by 2. And we can get then the total time that the shot put is in the air. So I can say, well, the Vy at the apex, this will be my how fast equation, going to be my initial Vy plus then At. Because it's in free fall, then that A is really G, negative 9.8 meters per second. So at the apex, again, my velocity in the Y is 0. But my initial velocity was 10.7 meters per second. So I'll say minus 9.8 meters per second, and times t. And that'll be our apex time. So I can run through the calculation there, put the 10.7 on the other side, divide that by my 9.8. I get an apex time then that's equal then to 1.09 seconds. All I have to do then to get the total time is I can multiply that by 2. And I get a total time then of 2.18 seconds. So the shot put's going to be in the air 1.09 seconds up, 1.09 seconds down, a total of 2.18 seconds. So it's going to be moving vertically for that amount of time, up and down, and it's going to be moving horizontally for that amount of time. We need that total time then to find part B, the range. The range then is how far forward. Let me change colors again. How far forward then the shot put goes. So the range represents really the final position in the x direction, subtract the initial position in the x direction. So that's going to be our displacement really in the x direction, which we're calling the range. So the range really represents the displacement, xf minus x sub I. And we know then it's traveling in the horizontal direction, the object the shot put's traveling with the constant velocity. So we have CV. So we know then x sub f equals x sub I plus Vx times t, where that time is going to be the total time. Okay, well, xf minus xi, if we put the xi on the other side, that'll be our horizontal displacement or our range. So really we're saying then the range is then this Vx, that's going to be our 9 meters per second. Remember, that's our initial velocity in the x direction, and that vector doesn't change. And then we'll take that times our 2.18 seconds. That'll tell us then how far the shot put goes forward. And I get around 19.7, 19.6 or 19.7 meters. Okay. And I think I have the answers down here. Are we doing everything right? We're getting the time and we're getting the range. It says here the actual throw was around 19.1 meters. Finally, we want to get the maximum altitude. Okay, so this maximum altitude on my drawing, that maximum, let me change colors here. That drawing then, yeah, let me just choose this one. That's going to be right at that apex. So this would represent the maximum height. So it's going to start at the ground and go up to this height, and that's going to occur at this apex time. So we really want to so that idea here really is a how far, but it's a how far upward, right? So we can say, let's just kind of make a little region to work here. We can say really, we can use really our how far equation, and this was our generalized how far equation. Okay, now we can use it for our vertical and use our vertical symbology really. We have y sub f minus y sub I. So we change these to y's and put the x sub I then on the other side. That's going to really be our vertical, our maximum height. And this will be VI y times then our apex time plus 1/2. It's in free fall, right? So that A is going to be G and T squared. And again, that's going to be our apex time we'll have to square that sort of variable. So our maximum height at that apex, that'll be our VIY, that's our initial velocity in the y direction, 10.5, 10.7. And we'll take that times our apex time, which we said was 1.09, plus then 1/2 times a negative 9.8 meters per second, then times 1.09 seconds, and then we have to square that. So again, this chain of calculations, there's a lot of things to do here. You want to be really careful here. But let me throw everything into my calculator. We have 10.7 times, let me clear my calculator, 10.7 times 1.09. Okay, I get 11.663 meters. And then we've got 1/2 times our 9.8 times our 1.09. I want to square that, and I get around 5.82, maybe 2 meters. So we have 11.663 minus 5.822. We get around 5.8 meters. And that's what I'm getting here on my answer. Now we do have a few more pages here, but these are type 3 problems, and I'll work those on another video. So again, there's basically a couple of type 2s I worked. And again, you can kind of use symmetry here to help you. Hopefully that helps, kids. We'll talk to you later. Bye.